Hi, good evening, all. This is Vishal Singhal from Selfstat, your host for today. So we have Mr. Amar Singh. He's a deep learning researcher in our Selfstat AI lab, and he's going through reinforcement learning experimentation these days, and will be taking us through optimal policy in RL using the right method. So, Amar, are you ready?
Yeah, I'm ready. Good evening, all. I'm a researcher at Cellstrat. Uh, yeah, please.
So, transferring you the control.
Yes, thank you. Mm, yeah, yeah. Good evening. Hope all of you are able to view my screen.
Yeah, go ahead. Thanks.
Yeah. How, now we'll talk about optimal policy. Optimal policy is where we are able to find a right path. Now, for example, any reinforcement learning problem we have where we have to attain certain goals, majority of the situation. Some instances, the goals are not so clear because it's a continued task, like in a self-driving car. But generally, there are some games where there is a goal and there are various means or various pathways where we call those various policies to reach that goal. So optimal policy is the best policy, is what we are, the best part to take towards reaching the goal is referred as optimal policy, referring to this first sentence, the best path. Okay. Also, policy is something which is mapping from states to action. Now, for any MDP is something which defines a complete state or a complete environment. If you look, MDP helps define it. We'll talk about it more. MDP helps define there exists an optimal policy that is better or equal than other policies. Optimal policies achieve the maximum state action values. Now, uh, that is reaching the goal. There are various trajectories, various pathways reaching the goal. So the particular goal, particular pathway, we can refer it as optimal policy. And these optimal policy, the pathway passes to the various states. So the whichever states have got maximum values, state values, or we also talk about further, we will also talk about action values, but as of now, let's limit ourselves to state values. So whichever path has got states with maximum values, by default, those can be referred as optimal policy. So it's synonymous when you talk about optimal policy or the best path is same as having states with the maximum value. Okay, let's look at the last sentence. Optimal policy, we put it as that pi and star is synonymous with deriving the maximum state action value function. That means we are able to derive the maximum state value function, the maximum value. That itself also is referred as optimal policy. Let's move ahead. Now, before we talk about finding out finding the optimal policy, there are various methods. But before that, we need to slightly know about two things. We need to know about the environment. What is the reinforcement learning environment? We'll spend a minute or two on this. Then we also need to know on this next slide, Bellman expectation equation. So these are the two things which will help us finding out the further discussing about our optimal method for the optimal policy. Now, MDP is something which defines the environment. That means if you take off any game, right? Let's think of simple things like a chess game is there. Chess game, you will have a checkered boxes of 8 cross 8, that is 64. That means assuming or you have a grid world of 4 cross 4. Let me just present it for you. Yeah. you have a, yes, you have a grid world. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 16 say. You have a grid world. You're starting S1, S2, right? And S16. That means this, if I call it a goal, right? So this kind of a thing, that means the pathway towards reaching the goal, each of this box, you call it a state. That means an agent. Agent is the algorithm or the player is as such here. So the player is moving across these grids, right, across these boxes. So each box you can refer it as a state. And then moving from one state to the other, right, there is some action to be taken. So that is what actions are, something which help transition from S to S dash. Okay. Next, in the process of transition and on taking an action, it reaches to the next state, and also in the process it gets some reward points. So MDP talks about states, that means the various positions where the player could have been placed. Then, okay, I just missed out on this probability. Now, let us take a state, a particular let us refer a state, this particular state. So there is a chance from here it could go in one of these four places, right? That means states to move to this particular state, 1 by 4 or 0.25, here 0.25. That means moving from one state to the other, there is a probability that is called a state transition probability. That means this is sometimes from S1 moving upwards, sorry, this is not S1, right? Moving upwards, downwards, left or right, various movement, it depends on certain probability, transition probability, that is one. Next, action, rewards. Now, discounting factor. Okay, just a moment. Okay, let's talk about discounting factor. Now, you are moving from state 1, state 2, state 3, state 4. In the process, you are getting reward R1, R2, R3, R4. Maybe let's take it same way reward, I'll just put it R5, R6, and then you are reaching. So in the process of reaching the goal, R1 to R6 or R7, this is the amount of all the reward what you are going to get, R1, R2, right? This is the total reward what you get. But being at the initial, at this current instance, we are not able to say if the reward R1 is immediate reward, but the next reward is not sure. When it is not sure, we discount it. When the further reward, more in the future, more the surety is more less. We are not so sure. That's why we discount it further. So this kind of a discount factor is also there. So these are all the things: states, action, rewards, state transition probability, discounting factor. These are all helpful for defining an environment. Okay. So this is referred as MDP. Let's move on to the next thing. Let's just a moment. Just
What happened, Amar?
I'm not able to move to the next screen.
I am not able to see your screen itself.
Okay, just a moment. Yeah, now?
Yeah. So you have to first convert your marker to normal mode.
Okay. Okay, thanks. Sorry. Please excuse me for this. Bellman next talk we talk about Bellman expectation equation. This equation helps to calculate the value of the state or an action. Okay. Before okay, let's not think more of the action value. We'll just talk about the state value now. Just a moment. Now, this is the state value. As I have just now referred, at each step we have a R1, R2, R3, R4. That is the reward in sequence as part of the trajectory and various states which we get. And that is further discounted as much more in the future, discounted. And all of this together, so that means the current reward is known to us very clearly. But the next is something we make a guess. And all of this is combined. That means that we refer it as bootstrapping, the concept of bootstrapping and combined. And this is referred as to the what reward you can get in the next step onwards. So this is called a concept of bootstrapping. And then this bootstrapping is also nothing but it gives the value of the next state, value of next state. So if you look at the current state value is what reward we get plus the value of the next state. That means when a person, when a player or the algorithm or the agent, when the agent takes an action, it receives a reward plus being in that new state value. So this is what all it talks about, Bellman expectation equation. That means the value, that means all the future rewards are clubbed together and presented as a value of the next state. Okay. So let's move ahead. Yes. If you look at an ideal RL trajectory, you'll have a sequence of states, actions. Now, but in real life or in real life problems, if you look at it, here we talk about states in sequence action, and for every action we get a reward, and then we arrive at the next state. Again, at that state, you take an action, then as a result of this action you get a reward and then you arrive at the next state. So this kind of a sequence is there. But if you look more clearly in real life problems or when you look at any game sort of a scenario, you are in state S1, there are chances that when you take action, you may take an action A1 or you may end up taking an action A2, and there is a probability attached to it, right? Probability attached to it, right? And then this is the state transition probability. Now, this probability, I'll call it as this is a state transition probability. Next, on taking an action, sometimes you may arrive at a next state S or S2 or S3. Okay, that means there are chances that when you take from a state, when you take an action, that means from a state you may take numerous actions A1, A2, A3, and there are probabilities P1, P2, P3. Okay, same way here from an action, when you take an action, you arrive at the next state. So here there is another probability which we call it as environmental probability. So there is one probability between states and action. This probability is because of the policy, and as a result, from the action to the next state, there is another probability which is because of the environment. So there are two sequence of probabilities which are there. Okay. So this idea will help us further to know about the sequence of states and actions. Let me just. Yeah. Yes. Here, if you look at it, the same thing what I've been telling. There is a state, and state from the state S. State S, we have got action A1, A2, or A3. Taking this action A1, A2, A3, there is a probability, different probabilities of all this. Okay, next. Being now this particular thing, this is referred as state. The darkened circle, darkened refers as an action. Same applies for this next figure also. Okay, that means from a state, there is a possibility you may take different action. And on taking a particular action here, you may arrive at different states. Okay, now, so that means now we have looked at two probabilities. One is a probability between states and action. This is the probability of policy. This is the probability of environment. That means this is nothing to do with the policy. That means this is the external situation which is independent of the defined internal game or the policy or the pathway what we are thinking of. Okay. So looking at these are two things. Okay, there's one more point. When we arrive from states to action, you see, V from the particular V is a state, right? Probability of, let us take a probability pi1, pi2, pi3, right? So this pi1 q1, right? Pi2 q2, pi3 q3. That means this is the probability. Okay. So sigma pi q1. Okay. Or I'll call it as I. But whereas in this case, okay, here this is a state value. This is the action value, right? Action value, right? For action value, when you take an action, you immediately get a reward, plus there is a probability of P1 that you may go to a next state, right? P1 that you may go to a state S1, S1, okay, S1 dash, P2, P3, P2 S2 dash, P3 S3 dash. That means when it comes to our state value function, no such reward is there, no reward immediate, right? No reward is received, but you translate to an state to an action, right? But when you take an action, you have a reward plus the state value. So this state value together, I'll just put it towards the left, q pi is equal to reward plus sigma summation of probability and the state value function. State value, yeah, we put it as B, sorry, B. I'll put it as I. Okay. So with this, now we know that states to actions. Okay, I'll use another color. Yeah. Here we have states to action. Okay. And here we have action to the next state. That means states to actions to again to the next state. So states to action, right? From actions to again possible states. And here there is a probability. Here there is a probability. In this case, there is also a reward which you get. Okay. So I think with these points, we are now prepared to look at the various methods for finding the optimal policy. Yeah. Now, the same thing what I had shown earlier, now it has been combined: states, action, action to the next state, or the next cases, the right side you have action to the states followed by again action. The sequence, it's an alternate sequence of states and actions. And for every state, the sequence of action may be more than one. Okay. So now we were talking of just till now we spoke about optimal policy, and then we are now trying to find out what is the best method to find the optimal policy. And before that, we just looked at Bellman expectation equation. We looked at MDP, MDP, that is defining the environment. Okay. Now these are the three methods what we have: dynamic programming, Markov decision process, temporal difference method. Okay. Now let us see what is the factors, determining factors where we use this particular methods. Okay. Now here we will spend some good enough time. Now in this case, complete knowledge of the environment. So whatever we are using, either these methods, dynamic programming or temporal difference or Markov decision process, depends upon the kind of environment. That means how much we are aware of the environment, what is the factors, what is our level of information what we have about the environment. Now complete knowledge of the environment, when sometimes the environment is there, we know the states, we know the actions, rewards, okay, we know all those, the MDP, whatever MDP, what is there. And then the transition probability, important thing is transition probability. That means from states to action, how we translate from states to action, the probability involved. So if we are aware of all those things, that makes a complete knowledge of the environment. If this is there, we are able to use dynamic programming. Okay, next. Some instances are there, we will not be knowing complete knowledge of the environment. We may be knowing states, we may be knowing action, reward, but we never know from moving from one state to the other, the state transition probability, right? State transition probability is not known. Sorry, probability is not known. In this case, we use a method called Monte Carlo method. Monte Carlo method. Now, when the state transition probability is not known, but we know all the sequence of states till our goal S1, S2, S3 up till the Sn, all the sequence of states we are aware of the actions and what is the reward which has been reaped. So that means this also refers to a terminal episode, that is sequence or episode where we have a start state and a terminal state. Okay, that means we are having a sequence of episodes, sorry, each episode, and such kind of n number of episodes are available, but only thing is we don't know within the episode, moving from one state to the other, what is the probability, what is the possibility, how that kind of information is not available. So here Monte Carlo policy helps a lot. Okay, and coming to the third one, non-terminal episodes. Non-terminal episodes, to give you one, it's a very prominent thing, we talk about this self-driving cars, okay, or some gaming experiences where there is no such end. You just keep playing and it keeps going, and there's nothing called an end of it. So such a thing is called a non-terminal episode. Okay. So in this case, also we may not, we don't know where it ends. Okay. So we need not have experience of earlier episodes also we may not know. So here we know the current state and the next state, some sequence of states. We don't know the entire episode, how many states are there. More, that means when you come to this particular state, you have information is much lesser. And this is where we use temporal difference method. Okay, well, let me make a quick recap. Dynamic programming, where everything we know about the environment, states, action, rewards, and how do we move about from one state to the other using the state transition probability. But when it comes to Monte Carlo method, we know states, action, rewards, we know the entire episode thing, but only thing we are missing out on the state transition probability. That means we are not able to say with that probability or cannot define a probability how it is moving from one state to the other. Okay. Whereas, and this is a terminal episode, that means it's a limited thing. That means we have a start state, end state. But when it comes to temporal difference method is the heart of reinforcement learning. That means any further in future more complex RL problems, they use temporal difference. So in this case, we don't have a limited, states are not clearly defined, need not have the experience earlier. What earlier experiences is also not known. Neither the transition probability is clearly known. Neither do we know that the states are entire episode is not known. Okay. So with this tree, a basic idea. Now let's look at each of the methods. Okay. So first we'll look at dynamic programming. Yeah. This is a method to solve complex problems, breaking down into sub-problems, and the solution of the sub-problems is combined to solve the overall. Given the complete knowledge of the environment, helps to complete dynamic programming helps to compute the optimal policy. That means, as I referred earlier, complete knowledge of the environment, states, action, reward, transition probability. That is, we refer it as MDP. Okay, complete knowledge of the environment is known. So it's only a matter that we are able to find out what is the best pathway to find out the optimal policy. Okay, now let's look ahead. Now, in this case, there are two aspects. One is policy evaluation and policy then improvement you have got. Okay. Now let me first this particular thing we first initialize. Let's talk an example. The 4x4 grid you take. Okay. Now 4x4 grid. Now let me just yeah. This is your start state. Okay. This is your goal. Okay. 4x4 grid. So we never know what is the pathway to take from this end to the other end. Okay. Now, as I told you, the optimal policy is something, the right pathway. Okay. The right pathway also is a pathway which will give us the maximum value, state value. Okay. That pathway involves states. A particular pathway, if I take, it involves, for example, the pathway is going this way. Okay, that means this particular pathway, this particular states, this particular SS, these particular states are the states with maximum value. Okay, so that is, and that will help us know the optimal policy. How do we calculate this? The state value function, that is what we will use Bellman expectation equation. Okay, now There are, as I mentioned, two probabilities we'll be using. We will be using rewards, state value functions. Let's look at it in detail. Yeah. Now, if you look at it, now we are trying to find out the value of a particular state. That means we are looking at one probability, right? That is the probability of the, which refers to the policy, and other probability which is because of the environment. Then once this is a state, after the environment probability, then the action has been taken, so you get a reward, right? Reward plus the value of next state. I think I'll just write this more clearly. First is one probability, this is policy. Another probability is the environment probability. Then the action is taken, for that particular action the reward plus the value of the next state. Okay, so no, value of the previous state. Okay, value of the previous state. Now let's look at it. Now let us take for example any particular place. Let's talk about this particular point. Okay, now what happens? Moving across left, up or down or left, these are the four possibilities of moving, four equal possibilities. That means that each probability comes out to be 0.25. That means 0.25 probability of moving this way, 0.25, 0.25, 0.25. Yes, so that means this is the 0.25, this is the environment probability. Okay, next comes, please excuse me, this is the probability because of the policy. This is internal to it, right? Next comes the environment probability. That means the external factors. Okay, I correct myself. Earlier, this probability 0.25 is the probability because of the policy internal within the grid. What is the probability moving across each of the other states? Okay, then comes the probability of environment probability. In this case, it is a sure case. That means action is taken. Okay, action is taken, the agent is surely going to move to the next state. There is no such possibility that action is taken, there is a two-way chances. It may reach the next state or may not reach, come back to the next previous state. Such a situation is not there. It is a sure case. So for all the practical purposes here, to make things simple also, we have taken the environment probability as 1, and that 1 you will not be able to see this here in the calculation. Next, okay, next, every action they take, they get a reward. Reward is calculated, taken as -1 plus gamma, the discount factor. I missed out. Discount factor is, that means the other value of the next state is discounted, discount factor. And for that matter, what we do, discounted means we it is a sure case. Okay, that means when we say 1, it is a sure case that whatever value we get is definitely going, you can account it for now. Okay, so 1 is the gamma value could be between 0 to 1. Okay, 0 to 1. So in this case, gamma value is 1. Okay, and then value of the previous state. Now, for example, let's look at it here. I'll just clear some of it. Right. Let me just be quick. Now here, I think we are trying to calculate for here. Okay. Now for this particular state, if you look at it, right, moving each of the case 0.25, 0.25, right. Next, for each of the case moving to, there is each of the possibility of moving that action. These are the possible rewards for every action. This is a possible reward. That means it can go up. That kind of action which will give a reward of -1, -1, -1. Next, then plus gamma into the value of the previous state. Previous state means in the previous grid. I mean previous iteration. This is K0 iteration. Previous iteration. We take the 0 value here, right? Yeah, clear with this? So these are the things which will come up here. 1, 2, 3, 4. Okay. So this is the result of this. Similarly, if you look at it here, let's calculate for this 1.7. Okay. Same way, 0.25 is the our policy probability. Then the action reward plus the value of the previous state. Now for this is one value, this is one value, and this is one value. And but when it comes this side, it will not jump out, but this same value -1 of the same current thing is taken. Okay, and in this case 0, -1, -1, another -1. So 1, 0 is there, followed by 3, -1. So this is how we arrive at the value function. Now, so n number of iterations, we are able to attain our values. Okay, that means the agent is able to learn how well to play the game. Now we have got the state value function. Now how do we decide what action, how the agent is going to move here? This is something which we have calculated, the state value function. Okay, moving from one iteration to the next iteration, what is the kind of state value function we have created? We are able to find out. Next is the agent has to now move, and also we have to now find out the optimal policy. That means we have to find out what is the pathway. Now let me just give an example. Here we use something called greedy action. Okay, that means action which gives the maximum reward. Okay, that means if you look at it, let's I think here is better. If you look at this particular box, right, this particular box, here I cannot make out. Everywhere it is the same reward, so it will take an action like this. There is a 4 possible actions it may take. Okay, let's come somewhere here, right? Okay, now, and please keep in mind that these values are negative. Okay, so negative means the least value, I mean the numerically least, right? Because of the negative sign, that's greater. Okay, so if you look at all these things, for -8.4, -7.7, -7.7. So that means being in this state, either it may go left or down. I'll give one more example. Being here, okay, being here, it may take either right or up. Okay, that means it will try to take an action which gives maximum reward. So when we are able to put this kind of action values or action, what it can take. Just a moment. Yeah. When we are able to take the action, we are able to arrive at this kind of a plan. Okay. Now we know at each state what is the possible action, what is the possible direction it can move. Okay. Now if you look at it, how do we define the optimal policy here? How do we define the optimal policy? Now, this optimal policy defining depends on this arrows, how they help us to find out which path to go. Okay, that is one way. Okay. Also, where do we stop? Now we have started with K0, 1, 2, 3, 10, and then it goes up till infinity. But if you observe from K3 onwards till K10, this grid, okay, it remains the same. It is almost the same, this grid. Okay, if you observe the arrows, this arrows, these arrows, okay, the grid remains the same. So this is where we can stop our learning process. So this is what gives us the optimal policy, and this is the same pathway if you are observing. Okay, this is the same pathway, or let's look at here. This is the same pathway. We have got the maximum rewards coming up. Okay. Just a moment. Yeah. Now what we have done, policy evaluation we have done. 1 minute. We have evaluated the policy here. Okay. Then after evaluating, we were able to find out the state value function. Now here we are able to evaluate left side. Right side, we are able to iterate. That means we are able to define the pathway the agent can take, getting the maximum rewards along the way to reach the goal. So this process of, there is something called policy iteration. That means we evaluate, then we iterate. That means we find out the value of each state across each iteration. We do it in sequence. Then at one particular point, we know there is a same grid pathways coming up. That is when we can stop. Okay. That is one way of iteration process. Another way of iteration process is value iteration. That means we are not finding out the iteration. We are not creating the pathway or trying to find out the pathway for each thing. I'll just go back now. In value iteration, sorry, policy iteration, we do this in sequence. 1, 2, 3, 4. Okay, in sequence. We do evaluation and iteration. We do in sequence. But when it comes to your value iterations, we are not going to do this at all. Okay. What we do in sequence, we do this 1, 2, 3, 4, 5, 6. Okay. And we see the state values, right? State values, if they are not much differing, if the state values are not much differing, that is when we can stop. Okay. And at that state, we go ahead and do only once iteration. So iteration is done in only once. Okay. So in your policy iteration, evaluation and iteration, number of times you do the evaluation, number of times you do the iterations are equal. Okay. Whereas value iteration, that means you're finding out the value here 1, 2, 3, 4, 5. Then you're stopping it. Okay. Then you're going ahead and doing the final, right? The final, you're doing the iteration. Okay. In value iteration, you do the iteration only once. Okay. Yeah. So as I said, policy iteration, sequence of evaluation and iteration sequence follows. Okay. Whereas then value iterations, only evaluation is done, final iteration is done only once at the last. 1 minute. Just. So in this case, what happened? V star is there. I'll call it as Vn. Vn minus 1. This is approximately equal. That is where we stop. and then do a iteration, right? As I said earlier. Okay. Yeah. So we just now looked at our dynamic programming. Now let's look at Monte Carlo method. Monte Carlo method is used when the complete environment dynamics is not known. You may be knowing the states, action, reward, but the state transition probability is not known here. This requires only experiences. That means we require a complete experience. That means a complete episodes starting from a particular state 1, 2, 3, that is the initial state, to the complete terminal state, that complete episode with a defined number of states. That complete is referred as one experience. So such n number of experiences would be helpful here. Applies only to episodic task, that is start state, end state. Uses the concept of incremental mean. We'll talk about incremental mean. No bootstrapping. There is no need of bootstrapping here, because everything, all the states are known clearly, all the rewards are known very clearly. We know what reward when we are able to get. There is never a need for bootstrapping. When we are not able to clearly guess, we use some discount factor, we use gamma, and then we do bootstrapping. But here we never need that. So Monte Carlo. Yeah. Now let's look at this same policy evaluation. Here in Monte Carlo, states, actions, rewards. Now you have this sequence of states, actions, rewards. Yeah, you have a state S1, S2, S3, right? S4. This is a sequence. But sometimes it happens that it will not be such a sequence. There are some chances that S1, S2, S3, then again it comes back to S2, then S4, S5. Okay, again maybe coming back to S2. So such kind of situations are there. Okay, so that means we are supposed to find out the state value. We are supposed to find out the state value. Okay, we require it, state value. So in that case, it's a confused situation. We have state S2 is coming once, twice, 2, 3 times it is coming. So here Monte Carlo has got two methods. One is first visit Monte Carlo, every visit Monte Carlo. In first visit Monte Carlo, it just considers the first time the state has been visited. Whereas every visit Monte Carlo, it considers, takes all the three, takes into account all the number of times it has been repeating and coming at the same state. That is what. So when we are talking about this every visit, when we are talking of every visit, we are talking of something called average. Average of the number of times, n number of times the state is visited. Okay, state is visited. So every visit Monte Carlo. So this is where we come across this average is incremental mean. Okay. Now the policy evaluation in Monte Carlo is Monte Carlo, as we know, the complete episode is known, complete sequence of states are known. But separate thing is in this, you have some states are repeated. When such a situation is there, then there are two methods we use, either the first visit or every visit. Yeah, one. Now this is a formula talking about incremental mean. I'll try to make it slightly simpler, the understanding part of it. Now, this is an old mean. Okay, this is, I will call it as old mean. Then what you have, this is the new data, right? New data. So to the old mean, how do you add up the new data? to arrive at this new mean. This is the new mean. Okay, the old mean is there, the new data, and then the new mean comes. Okay, so what I can say is, let me just make things J X A X B, right? X J, this is the mean, right? X J, right? So this is mu K. Okay, next. Then this particular, then you have the next thing coming up. Okay, xk is added. They take a mean of it plus the sigma of x1 to, or I can say j, up till j. Okay, now this particular thing is nothing but xj. Okay, is 1 by k, this up till this earlier old mean. This is the old mean, this is the new data, and this will give you the new mean. Okay, so how do I'll put it in some numbers also, 1 minute. Two plus 4 plus 6, right? Some mean is there, right? To this 2 4 plus 4 6 6 6 12 4. To this is your old mean. The new data has to be added. Okay, new data 5. This 4 divided by, sorry, please excuse me, I'm not able to get the max clear here. So I'll just say this is the old mean, new data, this is your new mean. Okay. Okay. Monte Carlo updates, that means it is able to get the new value, and this 1 by n, 1 by n, this is something to talking about the average, the mean, what we are talking about. And what they are doing is, when the data or the number is huge, 1 by n, the n value becomes huge. When the n value becomes huge, 1 by n, the entire value reduces, okay, as a denominator. For this becomes large, overall value reduces. So to avoid such thing, what they do, they replace it with a constant. So it is that, not that when it is n number of times the state is visited, it should not happen that the value is reduced. Okay, for that reason they use a constant rather than always going ahead always to divide it by 1 by n. So here this is the Monte Carlo updates, where new mean, new states, number of states, number of times the state is visited. Okay, as I have told you earlier, S1, S2, S3, S2, S4, S5, S2, the number of times the state S2 is visited. Okay, based upon which the number count is increasing, based upon which the value, this number is increasing, but the number goes up. To avoid that issue, they are using a constant. So this is all now helping us to find out the state values. State values, that means we are able to evaluate and give the state value. Now once the state value is known, we have to do the iteration. That means how do we take the action? We know the state values of each of the state. How do we take the action? So taking the action, we follow the same greedy policy method. Okay, the greedy action. That is, we see the next state, whichever particular being in a state, there is a possibility of going to the n number of states. So which particular state has got the maximum value? That means no other way it is looked at. It is only looked at which particular state is having a maximum value. That is the state the agent moves on. Okay, so that means this is what we have done in Monte Carlo policy evaluation. Policy evaluation helps us to find out the value of each of the policy. Once the value of each of the policy is known, we know the grid, we know the state values. Once we know the state values, now the agent has to take the action. Action it takes based upon whichever is the next state which gives the maximum value. That is the greedy action is what is referred as. Okay. So now till now we have seen dynamic programming. Okay. Complete model of the environment is known. Okay. MDP dynamics are known. Okay. We are able to evaluate. Then we are able to evaluate. We are using the Bellman expectation equation. Then we are able to iterate. That means we are finding out what is the best path. Okay. Now, process of iteration is sometimes we do evaluation, iteration at once. I mean, alternatively, and sometimes what we do only we keep on evaluating. Finally, once we iterate. So this is what is our dynamic programming. When it comes to Monte Carlo, it's a different thing. We don't have complete information of the environment. And a unique thing about is the sum of particular states are visited more number of times. So here is what we have, the every visit or the first visit Monte Carlo. Okay. But when we come talk about every visit, the concept of incremental mean is there. Okay. And then finally we are able to find out the value of a particular state. Then when it comes to iteration, taking the next action, it's a greedy policy, how an agent is able to take the next action. Now let's look at temporal difference. This is another very important method when it comes to finding out optimal policy. Here the agent learn directly from episodes of experience, but here it won't know the complete episodes. So here we use bootstrapping. Okay, we never know very clearly all the things. Okay, because and bootstrapping also involves that we are guessing out something of the future. One step actual return. Okay, I'll talk to you about one step or actual return. Okay, now before I talk about this example, imagine you are moving in a metro. Okay, and at any point of time you want to know how far is your destination, you will not be able to say. Okay, you will say, okay, let me see which is the next station comes. I'll be able to know which next station. Based upon that, I'll be able to tell how far is the destination. Okay, that means I'm able to predict about the future just by knowing the next stop. Okay, at this particular thing, I am now the metro is moving up between the two stations. I'm not able to guess out where my destination, how far it is. So I'll say, okay, let me see, let the next station come. Once I know that, then I'll be able to predict. So that is what you can simply take it as. It's a one step actual return. The next step is you tell me, or I am able to reach the next step, then I'll be able to rightly guess. Okay. So let us look at this quick example. Now a person starts from office. His time to reach home is, he estimates, he predicts that it may take 30 minutes and the total time is also 30 minutes. Okay. Then what happens by the time he reaches his car and things slightly late, 5 minutes he consumes. But now he says because it's taken 5 minutes and it's raining, he'll say, okay, from now onwards, I will take 35 minutes. So overall time, he says, now I will, overall time it took for me is 40 minutes. Okay. Then he now starts driving. That means from the start, he's consumed 20 minutes are passed. Things seem better. He says, okay, now things are better. It is only going to take 15 more minutes. So estimate further comes down. Okay. So in the sequence, what is happening? As at every step, his time has elapsed. That means from the start state, so much time has elapsed. At this is a new guess is making, right? New guess is making. This is all what the new guess is making, right? Then this is the total, right? This is the total time. Okay, that means based upon the past, how much time has been consumed based upon his guess, the total. Okay, now let's look at Monte Carlo, right? Temporal difference. Now, temporal difference, what is that? Just now, as I told you, one step. He is at the start, he said 30 minutes, okay. But the next step, it is 40 minutes, okay, if you observe. That means so much is the correction he has to make, okay, he has to correct. He'll say, okay, 10 minutes is what is the correction I have to make, okay. He just has seen the next step and made a correction, okay, next. But when it comes to Monte Carlo method, overall consumed time is 43 minutes. So Monte Carlo takes complete episodes, right? Considers complete episode, right? That means the total time is 43 minutes. That means earlier he made an estimate of 30 minutes, but overall time is 43 minutes. Okay, next he made an estimate of 40 minutes, overall is 43 minutes. That means the correction factor, okay, is with reference to the complete episode. But when it comes to the temporal difference, it will just look at the next step and make an episode. Okay. Now, for example, I'll put one more example here. When you are happen to travel somewhere and you're the cab or the auto person, you ask how far is the destination, an experienced auto guy will be able to say, will be able to tell you. But some person may say, I have to travel the distance, or I have never traveled there, I have to travel, then only I can say. Okay, so that means Monte Carlo method, similar like that, it will require the complete experience, then only it will able to say, otherwise it is not able to say how much is the time it takes. So it requires the complete experience. Okay. Yeah, so here we talked about one step, right? So as a person, I may say, let me see the next station, then I can say where the destination is. Okay, so sometimes some particular algorithm says, okay, let me see the next two stations, then I can say more clearly where the destination, more clearly I can make a prediction. So that means one step prediction, two step, or n step prediction. But n step, once you know everything about all the steps and then you try to predict, that is nothing but a Monte Carlo method. Okay, that means you know all the prediction, all the past experience up till the end steps you know. Okay, so normally TD we talk about one step, but some instances they may use 2-3 steps also. Returns for n step. Okay, now we will just talk about one step. Let's talk of only the one step. One step is TD, and the complete, when we talk about right, one step is TD. This is what we look keenly, and this is the Monte Carlo is the entire episode experience. Entire experience is required. Okay, now here only one step, just then T and the next state. Okay, what is the reward and the next state value? N step temporal difference defining n step. Let's not look into it now. Temporal difference, more than one step. This is n step when we talk more than one step. Now when we are talking of this taking n step or one step thing, then there is a concept of exploration and exploitation. Okay, that means exploitation, how it goes. How much the agent is aware of the next state. If he is aware and he is confident and he doesn't want to take risks, without known information, known awareness, known information, he is able to optimally utilize it. That is exploitation. Now, but there is some instance he may need to take a new step where he is not aware of. That is exploration. Okay, so there is a chance that a known thing or some quite often examples is this restaurant, a known restaurant they go. Okay, there's a sure case that they will find a good food. Okay, but there are some instances it's better to take a chance. Okay, some experimentation, going to a new restaurant, you may get a better food. Okay, or you may have the other way also. Okay, so there is always a need to explore and exploit is we try to be safe. Okay, now uh, as per experiences, if you look at it in iteration, and when it comes to experiences and iteration, in the first iteration, okay, first time you enter a city, majority of the time you don't know anything much. Okay, so that is when you are trying to do exploration. Okay, so as the number of iterations happen, the exploration is not much, more of, I mean, exploitation or more of the known things we try to play. Okay, so I'll give you more clearly with reference to this small code which is there. Now, see, one is what is this epsilon, right? Epsilon is something is equal to the iteration 1 by I. If it is I is equal to 1, epsilon is equal to 1, right? I is equal to 2, epsilon is equal to 1 by 2 or 0.5. Okay, let's leave it there. Right now, what we do is, how do we define how to do this exploration or exploitation? They define some random variable. Okay, some random variable, say whatever 0.6, I'll take it, right? So in the first case, if you see first iteration number 1, epsilon value is epsilon value is greater. Okay, epsilon value is greater. So compared to this random epsilon, so in that case, it will take random action, right? Just put it here. Epsilon, right, is greater than this random value. Okay, so in the first iteration, what happens? Epsilon is greater. So as I said, initially random value, and there is more of exploration. Yes, as it comes more nearer, n number of iterations, right? E3 is equal to 1 by 3 or 0.33. Now in this case, what happens? This random value, okay, is greater than our 0.33. In that case, now is where the agent is more experienced, is able to take greedy action. That is, it is able to do exploitation. The known things it is able to exploit. Okay, so that means this is a particular algorithm defining a random value. We are able to create a good algorithm or a good code where we are able to say how best to do this exploration and exploitation. Okay, yeah, yes. Now when it comes to, now we were talking about how do we, when it comes to finding the state value, right? evaluating a policy, evaluating the state value. This is what we have done. We have taken one step in a TD method, one step, evaluated it, and in the process of evaluation, the next thing is we want to take the next step. Okay, it depends on either we explore or exploit. Okay, and there is some amount of experimentation, but still we are able to define it in the form of a code using some random value. Okay, now when it comes to control, that is, now we know what is the action to take. Okay, now we know the state value function, what is the action to take. Okay, that is the control methods. So one is straightforward, we have one action state and the next action, right? I'll just give you in this, it's a simple sequence, right? It's a simple sequence we follow, right? One action state and then next action next action, right? But in this case we see from an action state next action, we say which is the maximum, right? Which is the maximum? Maybe this particular thing is the maximum, this particular action we will take, right? This is having a probability of 0.6, right? 0.6, right? 0.3, 0.1. So with maximum probability, right? As I told you, there is something called environmental probability. When that environmental probability is there, okay, in all the cases we never talked so much about environmental probability, because that is, if you look at in your dynamic programming, we talked about probability, but state transition probability, that is a policy dependent, but nothing external. But in this case, temporal difference method, the state or the within the policy, we are not able to, much of the information is not clear, so much of the thing depends on the environment also, environmental probability, and that is something which influences the action. Okay, so here we take the maximum, and in this case, if it is, this is action a1, a2, a3, probability is 0.4, 0.3 and zero point 0.3, then we do, right, we take a average or summation of it, 0.4 a1, 0.3 a2 plus 0.3 a3. So these are the three ways which we take next action. We have to take 1 minute. We take the next action or the next sequence of action, right? So these are the three methods, 1, 2 and 3, right? In this case, it's a simple sequence. In this case, we take the maximum probability. In this case, we take a summation or summation of probabilities. Okay, so this is where we take, and if you observe in the earlier dynamic programming or Monte Carlo, we have used our greedy policy, greedy action. Okay, greedy action. But whereas in temporal difference method, we are having, these are the various other options. Okay, and temporal difference methods are used quite often more high-end games, or you have automated cars. All these instances, more temporal difference comes into place, because these are all the high instances where the environment is more dynamic. We are not aware of much of the information. Yeah. So with this, now we have covered all the three methods, right? Okay, I'll just take 2 minutes to give you a quick recap of what all has been covered. Then what we will do, we'll look at some part of the code which I will show you. I'll just take a quick recap of whatever we did, right? First, we talked about optimal policy, right? Best pathway, where optimal policy refers to your value maximum value or maximum state or action value. Okay. Next, we talked about MDP dynamics, that is, which defines a particular state environment of an agent. Then we talked about Bellman expectation equation. That means this is what very helpful for us to find out this is the mathematical calculation which we require to find out the state value or action value. How do we calculate? These are the equations. Okay. Then we talked about the trajectory, but the trajectory is ideally not in a straightforward way. There are a sequence of states, multiple actions, and for a particular actions, multiple number of next sequence of states. Okay. So then, and also here we talked about two sort of probabilities: policy probability, environment probability, and we talked about that the rewards are received only when on taking an action, not from state to action, but from action to the next state. Then combining states and actions. Then we talked about, that was a prerequisite to think more about this, what method to use. So these are the three methods which we can use to find the optimal policy: dynamic programming, Markov decision process, temporal difference. Okay. This dynamic programming, complete knowledge of environment is required, right? And Monte Carlo method need not have the complete, but complete episode is known. Okay, entire episode, limited episode, number of states is very clearly known. Whereas the temporal difference method, temporal difference is a huge subject further. Okay, temporal difference method, where the environmental dynamics are huge and you are not so clear about the environment. Okay, and it's non-terminal episodes. In dynamic programming, here we know everything about the environment. Okay, we are trying to evaluate a policy using Bellman expectation equation. At every state, we first initiate it. Okay, then involve the two probabilities, involve the state values of the previous states, and then work it out. Then after policy evaluation, we improvement. Okay, and then there are two ways of iteration: evaluation and improvement. That means first we find out the state values, then we say what is the best pathway to take, or sequence in we do in policy iteration. But value iterations, we don't do all that. We simply calculate the state values of across every iteration, and then at final stage where the state values are similar across two iterations, that is where we stop. So Monte Carlo, we talk about having entire sequence of states we know, but only thing is probability, state transition probability is not known. Okay, so in this case, some states are visited more than once. That is when first visit, every visit comes. Then because every visit comes, we talk about average, we talk about incremental average, then incremental mean. Then how do we update and calculate the state values? Temporal. Then here we find out the state values. But when it comes to the action to be taken, we use a greedy action here also. Temporal difference. In this case, it's an unlimited environment. Okay, we don't have the terminal state. And I give an example of that train. The metro. You can't at any point of time predict. Okay, you have to see that next station if I reach, then I'll be able to more confidently predict about my final destination. Okay, then we talked about one step, and if it is an n step, it is nothing but the entire episode Monte Carlo. Okay, this is, we talked about exploration, exploitation. Okay, then when it comes to control, that is, in the earlier two methods, the control was to a greedy action, but in this case the control is to using maximum probability in Qmax, Q learning, or sometimes they use the summation of probabilities in SARSA, expected SARSA, whereas in SARSA it is a straightforward. So with this, we conclude. I'll just take you through some code, not much. Yeah.
Audience, any questions at all? So if you have any questions, please ask now, unless you want them to show the code. Go ahead, Amar. Nobody's asking. Thanks.
Oh, okay. So I have this temporal no, not temporal. First, I'll talk about dynamic programming. Okay. Dynamic programming, we talk about this grid world. Okay. Now, remember just a moment. Yes. Dynamic programming, we talked about the grid world, right? 1, 2, 3, 4, right? So we are trying to find out the values, initiated it with 0, right? Across K0, K1, right? This is what we found out. Then after finding out, we did the evaluation, right? Then iteration we have done. When we do the iteration, what happens? It gives the arrow, right? This is how we move out from ones. So this kind of iteration, right? It talks about the distribution, policy distribution. Let me try 1 second. Yes. See, we have this grid world. We import this grid world. Now I'm not going to run this code. Then in each, as per that grid world, 16 grids, if you remember, right? That means 16 discrete states are there. For each state, there are 4 discrete actions. Okay. No. Yes. Then we first talk about policy evaluation. We have a discounting factor, right? We define something called theta. Theta is such a small value. Okay. What is the advantage of theta? Theta is discounting factor, I told you, gamma. But uh, theta is something I told you in value iteration at one step after n number of iteration, it has to stop. So that means value of a state in one particular iteration and the next iteration, that difference, if it is less than theta, that is where it has to stop. Then we start with the random policy. Okay. Then now see, initially, if you look at it at every state, okay, random policy, that means being at the first state, there is equal possibility in the first state, left, right, up or down, right? Easy possible, equal probability is there everywhere it can go. Okay. Then further, the value function is calculated after n number of iterations, and it has stopped here because based upon the theta, right? Theta, it's this and the previous value, it's almost lesser than, the difference is lesser than that. Okay. Next, policy improvement. Okay. Now that means which is the best pathway. Now this value is known. Okay. After knowing which is the pathway to go, right? Now see here, minus 13 down here, right? Reshaped grid. Minus 13, minus 17, minus 19. Okay. So in the minus 13 to minus 17 it goes. That means whichever is there having the maximum value, that is where it moves. And how do we come up with that? Now see here. So your Now, I think there are two ways you can see, right? 0 is up, 1 right, 2 down, 3 left, down here. Okay. So that means the 4 by 4 grid, if you look at it, 0 up. Okay. Or let's start from down here. 0 is up, right? Then 2, 2. Okay. Down it goes. Okay. Next 1, 1 is right, 1 again right, then 0 up. Okay, so this is where it goes. This is one way. Another way is policy distribution. So based upon, in the first there are 4 possibilities. So first one, if it says it is up, next case it says right, left. Okay, next it says left, next it says at the third position down. So this is where you are able to find out what is the pathway it is able to find. Go. Define value iteration. Again, this is the same theta we have defined, discounting factor 1. Okay, this is, I think, the final thing. Finally, we are arriving at this. Okay, this is the optimal policy after a number of iterations. So this is about dynamic programming. Okay, I don't have the code ready with for Monte Carlo. Temporal difference, I will show the Q learning part. Temporal difference, we import the required libraries. Temporal difference, we have something, it's a different thing. What we can say, it's also a grid of 48. You start with 36, and this one. Yeah. You start here 36 and you are expected to reach here. Okay. And you are never not expected that you should not be reaching here. So this will be the optimal policy, right? But it is always a risk that you may fall down here. Okay. And then you may be pushed back. For that reason, it is always better they move either traveling from here or something this way. Okay. So this is all about this. So at each state, you have again 4 possibilities, right? There are 48 states. If you look at 0 onwards to 47, 48 states and 4 discrete actions in each case. Okay. So here we'll talk about policy evaluation, then SARSA, Q learning, and SARSA max, expected SARSA. Okay. So first we talk of SARSA. SARSA is the sequence of states, action, states, and again action in that sequence. Okay. So it's a simple sequence it is in SARSA. So alpha, we have gamma, Q, state action, rewards, next state, next action. So these are all. And then we define, when we are going with this, we know exploration or exploitation. This is where we define the random number. Okay, that means across each iteration we know whether we explore or exploit. Okay, then we are able to complete our thing. SARSA number of episodes, it's defined. Then we are able to plot the graph. So after some episodes it attains the optimal policy, then no further improvement is there. Then Q learning is nothing but SARSA max. Here we refer it as referred as SARSA max. That means max is the maximum of the probability. Okay. Here also we run the code, then we check up. Here also after a number of episodes, it attains, then it is stable, no further improvement happens. Then expected SARSA. Expected SARSA also we run it. Then we have, in this case, expected SARSA, there is a lot of variation. Initially, optimal policy is attained, then across the time it may increase or decrease. So with this, we have seen the code of dynamic programming and also temporal difference. Okay. Any questions if you have, I can answer.
Audience, any questions for Amar? So no questions are coming. So I believe he has been very, very detailed. He's very, very maths inclined. So I was feeling that a lot of people who joined earlier, they dropped out, I think, after 25% of the webinar because it was very maths inclined. But he was explaining very nicely. So I'm sure whoever stayed has been able to understand this. So this session was being recorded and will be made live on our Self-Start YouTube channel in 2 to 3 days time. So thank you all for attending and have a good night to all. Good night to all in India and good day to rest of the world. Thank you.
Thanks. Thank you so much. Thanks, Vishal. Thank you.
Thanks a lot.